Let us meet again in our lecture number 2 for electrochemistry. As I have already said, my name is Tapio Gwamore. I will be offering you lessons for chemistry. So now we are on lecture number 2, in which we are now going to switch on to the processes that take place in our galvanic cells. These galvanic cells themselves, they can also be called a Daniell cell. This one is after a chemist and a metallurgist was called John Frederick Daniell, who discovered this particular cell in 1836. So the diagram which you see is a diagram of the galvanic cell. So now on the description of this particular cell, we actually see to it that the cell consists of two half cells, the zinc half cell and the copper half cell. In the zinc half cell, there is a zinc rod, as you can see, which we call a zinc electrode in a solution of zinc ions. Normally we can use even zinc sulfates or zinc nitrates, right, of concentration 1 mole per cubic decimeter. That is the standard concentration. And in the copper half cell, there is a copper rod, which we call a copper electrode, which is dipped in a solution of copper ions of the same concentration, that is 1 mole per cubic decimeter. Right? When the switch is closed, we see to it that a redox reaction takes place in the cell. The reaction taking place in the zinc half cell is our zinc solid, which is our zinc electrode here, is going to be converted to zinc 2 plus into 2 electrons. So as we can see, we can actually say that this one is an oxidation process. So the zinc serves as the anode. The reaction which takes place in the copper half cell is our copper 2 plus 2 electrons. We can form the copper solid. This one is a reduction process, so the copper serves as the cathode. So as we can see here, we are forming more of the copper, so we are going to have an increase in mass at the cathode. So we are having a deposition of copper on our copper electrode. But on this side of our zinc electrode, we are going to see that our zinc is going to decrease in mass. Why? Just because our electrode is being oxidized to zinc 2 plus. These by losing 2 electrons. These 2 electrons which are being lost from the zinc electrode are the ones which are being gained by the copper 2 plus ions, and in the process we are going to form the copper solid. And now we have the movement of these particular electrodes, that is from the anode to the cathode. That is the direction of movement of our electrons. Therefore, we are saying that our electrical current is moving from the anode to the cathode. So, in order for us to choose the two particular reactions, saying this one is an anodic reaction and this one is a cathodic reaction, we are going to actually explain this one explicitly under standard reduction potentials as to why, when we have the connection between our zinc half cell and our copper half cell, our zinc is at the anode and our copper is at the cathode. Right? At the copper electrode there, we have already highlighted that our copper ions from the solution gain these particular 2 electrons, and we are going to have the formation of the copper atoms. Right? These electrons, as we have said, we transferred to the copper through the external circuit. So there is a current flowing in the circuit. There is equal number of electrons lost and the electrons gained, as we would expect to happen in a redox reaction. When this cell is providing a flow of electrons to an external circuit, the zinc electrode, which is our anode there, we have already highlighted that it is going to be eaten away, while the copper electrode, which is our cathode, is gaining layers of copper atoms. The cell will stop working when all the zinc has been eaten away, or when there are no more copper ions to be deposited. There will be a build-up of charge in the 2 beakers. It is for this reason that the salt bridge is actually included in this particular cell. As we can see, we have about 3 functions of our salt bridge, which we are going to actually highlight shortly. That is the function of our salt bridge. The first function of our salt bridge itself is to actually act as an ion exchanger. That is the first function of our salt bridge. So let us look on the functions of our salt bridge. Right? So we are saying number 1, we have saying that number 1, it acts as an ion exchanger. So this one acts as an ion exchange, meaning to say that we are having an exchange of ions from our salt bridge into the separate solutions. As we can see in this case, we are having the formation of some zinc ions. So we are going to have the accumulation of more positive ions inside this particular zinc half cell. So we see to it that the chloride ions are going to actually neutralize the excess zinc ions which are going to accumulate in this particular cell. Same applies if we go to the copper half cell. We see to it that we are taking a lot of these copper ions which are reacting with our electrons and forming more of the copper. So at the end of the day, we see to it that the copper ions are being removed from the solution, and we are going to have the accumulation of some negative charges. That is, we are going to have more of the sulfate ions inside here. So there is need for us to actually neutralize the excess sulfate ions. So they are going to react with the potassium ions. So therefore, we're going to have the removal of the excess sulfate ions. So that's why we are saying that our salt bridge here, it acts as an ion exchange. So let us have point number 2. That is, we have it separates the two electrolytes. So our salt bridge itself separates the two electrolytes, meaning to say that, as you can see, we're having our solution, which we have there, maybe zinc nitrate or zinc sulfate, and in this case maybe we're having our copper sulfate or copper nitrate. As we can see, we have they were supposed to separate the two electrolytes, that is the solutions which we have. So that's the main function of our salt bridge. So number 3, we have the function of our salt bridge, as we can actually see that our salt bridge itself completes the circuit. So we are saying that the other function of our salt bridge is to complete the circuit, right? So that charge can flow from one half cell to the other. As we can see, if we didn't have a salt bridge here, in this case, we were not going to have the movement of our electrons or our electrical current from this half cell from this particular half cell into the other half cell. So those are the functions of our salt bridge. So the overall reaction which we are going to have, which is going to take place, we are going to combine the two particular reactions, and then if we combine them, we see to it that we are going to have the formation of our overall reaction. So we have said that in this particular case, we're having our zinc solid being converted to zinc 2 plus 2 electrons. This one is an oxidation reaction. And on this side, we have the copper 2 plus 2 electrons combining together, forming the copper solid. So now we are going to balance our chemical equation by the issue of electrons. So the electrons are going to cancel each other on both sides, and at the end of the day, we are going to have our zinc solid plus the copper 2 plus aqueous ions. Then at the end of the day, we are going to have the zinc 2 plus aqueous ions plus the copper solid. So this one is the overall reaction, which we call